Hello friends, this video on coordination compound part 18 is brought to you by examfear.com. No more fear from exam. So if you see in square planar, the splitting is in this fashion. Some dx square minus y square is here, dxy is here. So the splitting actually depends on the orientation of ligands. So in fact, most the other geometry also you see, the splitting is different. Okay, so but we'll focus only on the tetrahedral and octahedral splitting in this syllabus. Let's talk about the color of the coordination compound. So we have till now seen that the color in the coordination compound is because of DD transition. In the last chapter we have seen it. But the question is why? Why there is a DD transition? See, the d orbitals are of same energy. Why will the electron move from here to here? What is the need of this electron to move from here to here? There is no need, right? So if the d orbitals are of same energy, then the dd transition will not happen. dd transition will only happen when these d orbitals are of different energy. Then this electron will move from here to here. Okay, so this dd transition actually happen only in presence of ligands. Please note this. Only in the presence of ligands this dd transition happens. Okay. When the ligands are present, the degeneracy is lost and you have something like this. Then only dd transition is visible, else it is not visible. A good example is copper sulfate, if you see, is white in color. Why? Because this is not a coordination compound. But if we talk about CuSO4.5H2O, here my water is a ligand, is a coordination compound, this is blue. Due to presence of water as a ligand, the degeneracy of d orbital of copper is broken and we have something like this, and you see a dd transition. But in this case, of copper sulfate, the d orbital is something like this. So there is no color, but in this case there is a color. Hope you are trying to connect the dots. The dd transition which we discussed in the last chapter extensively for color is all because of presence of ligands. If there is no ligand, there is no dd transition. Because the presence of ligands actually helps to break the degeneracy of this d orbital, and that is the main reason behind the color. Okay, if they are of same energy, for example in this case there is no it is degenerate and there is no transition, no color. Okay, for example TiH2O6 with the +3 charge. Titanium has +3 charge here. If we talk about titanium +3 charge, the electronic configuration is 3d1. Titanium +3 charge is 3d1 because titanium is 3d2 4s2. +3 is 3d1. So if we talk about this, and this is, since it is 6 electrons, is octahedral, so it will be split like this. This will be T2G and this will be EG. Okay. Based on octahedral and tetrahedral only we can decide on this. And then only one electron here. So if you see, there is a scope for this electron to move here. And thus dd transition is possible and there is a color. Okay. Now the same, let's suppose we take this. So I had TiH2O6, the same compound which we are talking about, right? +3. If you heat this, it becomes colorless. So this is actually violet. But this is colorless. Why? Because now heat this, water is gone. The water is gone. Let's suppose this is Cl3. Water is gone, this becomes TiCl3. And there is no color. The water is removed, the dd transition is removed. Why? Because the degeneracy of d orbital is retained back. And in this case, the d orbital is something like this. In this case, d orbital is something like this. EG. Right? So in this case, there is no scope of transition, all same level. In this case, there is scope of transition, so color. Hope you understand the concept. In fact, as I told, the color is dependent on the ligand attached. Why? Because the ligands will determine the splitting, right? This value will be this much, or this much, or this much, right? This is talking about octahedral. This is T2G, this is again T2G, this is EG. So this delta naught is again decided by ligand. So for the same metal, if you have different ligand, you will get different color, because the energy required will be more, the wavelength required will be less, so it will have different color, right? Because I have told that energy is directly proportional to wavelength, E is equal to hc by lambda, right? So if the energy required is more, different energy is required because of difference in this value here, delta naught or delta T in case of tetrahedral. Different wavelength is required, that means different wavelength is absorbed, that means different wavelength is reflected, that means different color. These concepts we have seen in the past chapter. Okay. For example, nickel with water. So this is green, 2 plus charge here. And the same nickel with 4 molecules of water and one ethene diamine, right? Ethane diamine, actually, one diamine, the same plus 2 charge. This is pale blue. By the same nickel, same charge, but this time only 2 water molecule and 2 ethane molecule. This will again be purple. And the same nickel with no water molecule and only EN3 molecule will be colored because there is a ligand here. It is violet. You see different colors. Same nickel. Same all tetrahedral. Okay. So if you see, this is the electromagnetic spectrum and this is the visible spectrum range. So if this what do you call, I can say the wavelength, if this wavelength of the light is absorbed by a particular coordination complex, the remaining is reflected and it gives color. For example, if it absorbs yellow color, the coordination entity looks violet. If it absorbs green color, the coordination compound looks red. If it absorbs blue color, the coordination compound looks orange. If it absorbs ultraviolet color, it gives pale yellow. If it absorbs red color, it gives blue color. It absorbs pale green color, it gives purple color. So these are the combination we have seen, and these are the example of various coordination compounds. Okay, you see, same cobalt with tetrahedral, this is NH3 and this is CN, the color is different. Okay. So let's talk about some magnetic behavior. So this series is given to us. Okay. With this series, we can actually tell whether a compound is paramagnetic or diamagnetic. Example, if you see, let's see, take this compound CONH3 6 with the 3 plus charge and COF6 with the 3 minus charge. This has plus 3 charge and this also has plus 3 charge. Let's see this. Now cobalt has the electronic configuration of 3d74s2. So cobalt 3 plus will have an oxidation state of electronic configuration of 3d6. This is not required, just putting it. Okay, so let's and see, this is what? This is octahedral. So the splitting will be something like this. Okay, this is T2G and this is EG. Okay, where is NH3? NH3 is a strong field ligand. Please know it is strong field ligand, not a strong ligand. Strong field ligands. So first, second, see we have 6 electrons, right? First, second, third will come here, no doubt. Fourth electron will come here, right? Because strong field ligands, this energy difference is more. So it will pair. Okay, and thus it will form low spin and dimagnetic compound. We talk about COF6. Same thing is a F6 octahedral. So 1, 2, 3. This is a d orbital. This is T2G and this is Eg. Now, since this is fluorine, this is delta naught is less. So now again 6 electrons. Here also CO plus 3. Argon 3d6. So let's put first electron, second electron, third electron. Fourth electron will actually go here because the difference is less. Fifth will go here, sixth will come here. So if you see here, it is paramagnetic. Why? You see unpaired electrons, 1, 2, 3, 4 unpaired electrons. Here there is no unpaired electrons. And this is high spin. More unpaired electrons, high spin. Just so for this, to get this data, we don't need experiment. We just need this electrochemical series. And this is based on experiment at the end of the day. But this is a little handy. You don't need to know the magnetic behavior of all the coordination compound. If you just know the series, then you can actually guess the magnetic behavior of the coordination compound. Also the structure. So in the valence bond theory, you need to know actually the magnetic behavior of the coordination compound. Then you can guess the structure. In this case, just with the series, you can actually guess both magnetic behavior and the structure of the. Let's take one more example. So let's take this example. FeCN6 with 3 minus, and this is FeCN6 with 4 minus. In both cases, I'll show you that I am using the same metal and the same ligand. Okay, I don't need the series now, but there is a difference. So in this case, iron has a plus 3 oxidation state. This has plus 2 oxidation state. So Fe plus 3, if you see, is argon 3d5. This thing we have done in the last chapter. And Fe2 plus, if you see, is nothing but argon 3d6. Because Fe iron, if you see, the electronic contribution of iron is 3d6 4s2. So this 4s2, 2 electron will go. If you have plus 2 and 3 electrons will go, 2 from 4s and 1 from d to get this. Okay. Now, both are actually tetrahedral, octahedral, so I'll write it something like this. And both are strong field ligands, so this will be more. So let's see. Now we have 5 electrons, right? So let's put 1, 2, 3, 4, 5. Here we have 6 electrons. 1, 2, 3, 4, 5 and 6. Sorry, that's the mistake. Cn is a very strong ligand here. So you can't actually put these electrons here. These electrons 1, 2, 3, 4, 5 will come here. And these will be empty. Here 1, 2, or if we redraw it. If we redraw this. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay. So I have to put 5 electrons. Cn is a very strong ligand. So 1, 2, 3, 4th electron will come here. 5th electron will also come here. In this case, 6 electrons have to fill. First, second, third will come here. 4th, 5th and 6th electron will also come here because the delta naught is more. So thus, if you see, this is paramagnetic. And this one, if you see, all paired, this is dimagnetic. But here also we are actually using this series, right? That Cn minus is a very strong field ligand, so it will cause pair. We did a mistake here, so we were coming with the wrong conclusion, but we used actually this series. Okay.
Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.